This is a revision video for Physics Triple students only, and it's on waves for detection and exploration. We can use waves to detect differences in mediums. We can use it to explore structures, ones that we can't see. For example, we could look through a concrete slab to find if there's any cracks or faults in it. So what we can get a signal generator. We can send a sound wave down and it will reflect off any changes in medium. However, if I draw another concrete block that's got a crack in it, so there's a nice big crack, send the signal down, some of that signal will be reflected back. Some of it will be transmitted and then reflected back. So we'll get more than one signal. So if we looked at the screen on the signal, the sound would get a peak of reflected sound and would get another peak. Later on would get two peaks. Whereas if there was no faults, if we looked at our results screen, we'd get just one peak later on. One peak later on showing there's no faults. Here we've got first peak from the crack and then a second peak from the transmitted. And we can use our equation sheet to calculate the distance. So distance equals speed times time. And let's say it's taken 0.5 seconds. Let's say it's taken 0.5 seconds for that sound to travel, and it's travelled at a speed of 330 meters per second. How far away was that issue? We use our calculator. 350 times 0.5, 165. But because the sound has got to travel there and back, because the ultrasound's got to travel there and back, we have to divide our answer by 2. So 165 divided by 2 equals 82.5 meters. And obviously this is a very big number, so this would be something like the depth of soil or depth of concrete foundations, or it could be a ship underwater detecting the bottom of the ocean. Sound signal goes out, reflected back up, time taken, speed of sound is known. Any three of these numbers could be known. You'd have to rearrange, substitute into the equation and calculate it. So what is ultrasound? I've been using the word ultrasound quite a lot, and ultrasound is anything above what humans can hear, so 20 kilohertz. Anything above 20 kilohertz, which is the same as anything above 20,000 hertz. That is called ultrasound. Anything below 20 hertz is infrasound. Infrasound is less than 20 hertz. Ultrasound above 20,000, infrasound less than 20 hertz. So we can't just use ultrasound for industrial and sea imaging. We can also use it in medical instances for ultrasound scans of kidneys, of internal organs like the heart. We can also use it to scan for babies. So for example, if I was to draw a belly, and then within the belly we've got the womb and we've got a baby growing. The sound travels down. Every time it hits a boundary, there is sound reflected. Goes, hits a boundary, sound reflected. Goes down, hits a boundary, sound reflected. So this will show up every time there's a reflection. We'll get a different peak on the screen. So we'll get the first peak from some reflected off the belly skin. Then we'd get a peak from reflection from the womb. We'd get a peak from reflection off the baby itself. Then we'd get a peak from a reflection off the opposite side of the uterus, of the womb. So we can use these ultrasound scans linked with this equation to build up a picture of the baby internally using computers. So it's really, really useful. We can also use our knowledge of waves to apply it to the structure of the Earth. And the way we do this, or the way we've done this over the course of the world, over the course of history, humans have detected waves from earthquakes. So if I was to draw a crude model of the Earth, we've got the crust that's extremely thin, about 50 to 60 kilometers thick, not very thick at all. I've accidentally drawn it a bit thicker on that side. So we've got a liquid core and we've got a solid core. So S for solid core, and then we've got a liquid core here, and then we've got the mantle. And let's say we have an earthquake here. The epicenter of the earthquake is up there. An epicenter means where the earthquake starts. So the epicenter is up there. The waves, they radiate out from that point. We've got two different types of waves. We've got P waves, which means primary waves. So the primary waves, they are the first waves. They are faster and they are longitudinal. They're faster, they are longitudinal, they can travel through liquids and gases. So the P waves, they curl because they're refracting. We'll talk about refraction in a later video. They can travel through the mantle, they can travel through the liquid, and they can weakly travel through the center. So we get P waves that travel all the way through the solid core. After our primary waves, we have S waves. We have S waves, and they cannot travel through liquids and gases. Because they cannot travel through liquids and gases, they cannot travel through the liquid outer core. So the S waves again radiate out from the epicenter, but more slowly. So we've got this area here where we get S waves and P waves. And we get this area here where we get S waves and P waves. But we get this area down here where we only get the P waves, where we only get the P waves. And that's really important. So how do we apply this knowledge of S and P waves on the sides of the epicenter and P waves on the other side of the world, P waves only? How do we use this to describe the structure of the Earth? Well, because the S waves can't only travel through solids, because the S waves can only travel through, and they're slower, we know that the mantle is in effect solid. And because it cannot travel through liquid, we know that outer core must be liquid because the S waves cannot transfer through. So liquid, outer core, because S waves cannot transfer through. We know that it's got to be liquid outer core because S waves cannot travel through. Because we get weak P waves in this shadow zone, so let's label that up. Because we get weak P waves in the shadow zone, that shows that the inner core must be solid due to refraction. So P waves shows that the inner core is solid. That's due to refraction. And we know that the speed of the seismic waves, so these S and P waves are both seismic waves, that just means waves from an earthquake. And we know that the speed changes when it goes 50, 60 kilometres under the earth. So we know that the crust must be 50 to 60 kilometres deep. We also know that the waves refract. So we can use this refraction to measure and to determine how thick each of these layers of the earth are. And that's how we use waves for exploration and detection. It's very complicated, but the key thing to remember is that S waves cannot travel through liquid. P waves can travel through the liquid, so it's only the P waves that make it through to the shadow zone. The fact that S waves cannot travel through the liquid, that shows that the outer core must be liquid. The fact that P waves can travel through the liquid outer core and the inner core, that means the inner core must be solid due to refraction. And we know how thick the crust is due to the change in the speed of the seismic waves, and we know that the waves refract, so we can determine the density and the thickness of each of the layers of the earth.